Let's try this next problem. So, if the work required to stretch a spring 3 feet beyond its natural length is 6 feet times pound, how much work is needed to stretch it 18 inches beyond its natural length? Okay, and we're given that 12 inches is equal to 1 foot. So this problem's a little bit different than the previous problem in that we have a couple things. So this time they didn't give us the force. They gave us the work required to stretch a spring 3 feet beyond its natural length. Notice that the natural length is not given to us. So I don't even know what the natural length is. And actually, we don't really care about what the natural length is. So we know what? So what do we know? So the things that we know is that it requires a work of, a work of 6 feet times pound to stretch it 3 feet beyond its natural length. So basically, what I'm saying here is that if you have this spring, okay, if I wanted to do it 3 feet beyond, so this green part is 3 feet, the work, not the force, is 6 feet per pound times pound, not per pound. Okay, so that's basically what the work is. So they didn't give us the force. So what do we want to know? Well, we want to know how much work is needed to stretch it 18 inches beyond its natural length. Okay, so first let's start off with what we really know. So how can I relate work with the distance? Well, we know that the work is equal to the integral from a to b f dx. Now, do we know what f is? Well, we don't, because f is equal to kx. We know x in this case is 3, because I'm moving it 3 units beyond its natural length, but I don't know what k is and I don't know what the force is. But I do know what the work is. The work is 6. Okay, I know that the work here is 6, the integral. I know that I am moving it from 0 units all the way to 3 units. So this is going to be from 0 to 3 feet. And then what am I integrating? Well, the force. Well, the force is just going to be kx dx. Okay? All right, let me just take the antiderivative, okay, and see what happens. So 6 is equal to kx squared over 2 from 0 to 3. So I'm going to have 6 is equal to k. I'm going to plug in 3 squared over 2 minus 0 squared over 2. This is just going to go away. So 6 is equal to 9/2 k. Now I can solve for k. So let me multiply it by 2 over 9 to the other side. And what I'm going to get is that k is equal to 4/3. Okay, so now I know what k is. So I can figure out what f is. So my force is equal to 4/3 times x. That is my force. Okay, so now what are we looking for? So what we're looking for is how much work is needed to stretch 18 inches beyond its natural length. Now notice, everything that I've been doing has been in feet. Okay, this k was based on me calculating everything in feet. 18 is not in feet, so I gotta convert it. So I have 18 inches, and I know that in 12 inches there is 1 foot. Inches cancel out. Okay, and what I'm going to be left with is, what is this? 1.5 feet. Okay, so how much work is required for me to stretch this thing 1.5 feet beyond this natural length? Okay, so what is that going to be? Well, the work is just equal to the integral from a to b of the force dx. So it's going to be the integral from 0 to 1.5, this natural length. Then I'm going to plug in the f, which is 4/3 x dx. Okay, so this is going to give me 4/3 x squared over 2 from 0 to 1.5. That's going to give me 2/3 x squared from 0 to 1.5. I can only plug in 1.5 because the 0 is going to go away. So I'm I'm going to have 2 times 1.5 squared divided by 3 is going to give me 1.5 feet times pounds. So this is the amount of work necessary for me to pull this spring 1.5 feet from its natural length, or in other words, 18 inches past its natural length.